second part will be planar transformer design examples, step by step. I'm going to use a full bridge boost converters. And input voltage is 30 volt and output voltage varies from 50 to 100 volt. And turns ratio is 1:1, and frequency I'm using 100 kilohertz for example here. And the power is 500 watts. The booster inductor is 30 microhenry. Yeah. So this figure showing the circuit diagrams. And then the step one, of course, we need to draw the transformer waveforms, derive the transfer functions, and then here we're using 100 kilohertz for switching frequencies, because here we have 4 stages, and then the second stage and the fourth stage are symmetrical. So basically, the inductor frequency is double. So inductor frequency is 200 kilohertz, and here the T here is referred to the inductor frequency, so which is 200 kilohertz at here. So this is the waveform cross on the primary windings, and this is a waveform running to the primary windings, the current waveform running to the primary windings. And this is a magnetic flux running in the core. So when the voltage is positive, so the field, the B is rising up, and when the voltage is equal to 0, then the B kept constant. Because if you know the Faraday's law, voltage is equal to N times d phi by dt. So voltage is equal to 1, the rate of change of flux is equal to 0. So then the flux density is not changed, so keep constant. So when the voltage become negative, so then this will be declines. It's back and forth like this. Then the transfer function is here. So I'm not going to derive the transfer function here for you. I mean, but what I want to say is that when you design the transformer, you should be familiar with the circuit operation. You should familiar with the voltage waveform, current waveform, as well as the transfer functions. And duty cycle change from 40% to 70% is because of output voltage varies from 50 volt to 100 volt. And then step 2, we choose the suitable planar core size. The method, I mean, there are many different approaches to design the core. And here the approach I'm using is, I think this approach is better for a beginner. We choose the core based on the power level, and then and our design methodology is to make an iteration of the core size. We choose a starting point. If we calculate the core, if the loss is higher than the limits, then we can change another core. We can change another core size. So if we have a script, then we can easily to make this iteration of the core size. Yeah, I would like to say that in the beginning, the core you select may not be the optimal one, but when several iterations, it could become optimal designs. And here, I normally use the TDK data book from here. I also have a link for you. And there is a table we call the P transformer tables. And from this table here, we can see, for example, if we use a N87 material at 100 kilohertz, then we can choose those numbers are the power, the unit watts. So, for example, and EIRP38 is suitable for the power level around 323 watts. So, and the example here, we are going to design 500 watts. So basically, we can choose those different core types, 38 or 43. So, I mean, this is the starting point. So I'm going to select EIRP38 for starting point. And then if the core loss is over the limits, we can change another core. Yeah. So and now we got a data sheet from a TDK data book. The two important parameters, one is the cross section here, AE 194 millimeter square. Another parameter is volume. So the volume here is 8,440 millimeters cube. So we are going to use these two parameters to calculate number of turns and calculate core loss. So step 3, and still we're using the data book. We can also find the thermal resistance for this core, EIRP38. And the thermal resistance for this core is 20 degrees Celsius per watt. So normally we operate our converter or transformer below 100 degrees. So assuming that the ambient temperature is 25 degrees, then the maximum dissipated power is calculated 100 degree minus 25. So that is the temperature rise 75 degree. And we have thermal resistance of 20 degree per watts. So we get our maximum power dissipation is 3.75 watts. So this is our maximum. If our loss is more than that, so we need to change another core. So this is our methodology. So where is our optimal? If we choose this core, where is our optimal designs? So the optimal design for the transformer is based on the equation 2.2. So the 2.2 says that the winding loss, the optimal design, the winding loss is typically beta times the core loss. And the beta is one of the Stamets coefficients. So if you're familiar with Stamets equation for core loss calculation, there are three parameters, K, alpha, and beta. The alpha associated with frequency, the beta is associated with the flux. But the beta typically varies in between 1 to 3, depending on the core materials. So sometimes we see that 50% of core loss, 50% of winding loss, that's just assumption, but typically it's slightly, the winding loss is slightly higher than the core loss. So yeah, and here there is a catch. But if you're switching frequency at 100 kilohertz, the optimal frequency, optimal flux density could select the 150 millitesla. So later I'm going to prove that. So I mean, if you operate with different frequencies, then the B will be different. But 100 kilohertz normally is around 150 millitesla for optimal design. So step 4. So we're going to select the core material and calculate the peak flux density. When we select the core material, we compare the core loss from the data sheet. Around 100 kilohertz, we have several choice. For example, N87, N27, 67, and 97. So, but normally N87 nearly the same with N97 for 100 kilohertz. So here I'm going to select the N87 core material for my design, and then and then we can calculate the Stamets coefficient of beta equal to 2.5. And this is from the data curve fitting. So and if we know the beta equal to 2.5, we can get because the winding loss plus the core loss, so we get 3.5 core loss equal to the power maximum power. So we can calculate our core loss is 1.1 watts, and we know the volume from step 2, and then we can calculate the core loss density PV. Is the core loss divided the volume is 130 kilowatts per meter cube, and our transformer operates at 100 kilohertz. Then we can from this graph we can find out our optimal frequency. Our optimal flux is around 150 millitesla. The y-axis is flux core loss density, and the x-axis is peak flux density. So and this proves what I said before. At 100 kilohertz, the optimal design is around 150 millitesla. So once we know the B flux, B peak, then we can calculate the number of turns from Faraday's law. And Faraday's law says the voltage equal to N times d phi over dt. And we can apply the Faraday's law into the stage 2 here in the circuit operation. So at the stage 2, the voltage cross on the primary winding equal to V out divided N, and the dt is equal to 1 over d times t. And then delta phi is delta b times the cross section. So we know the delta b because delta b is 2 times b peak. And then we can calculate our number of turns. And here we should notice that our frequency, our T, is referred to the inductor frequency. And the spec we gave is a switching frequency, 100 kilohertz, and the inductor frequency is two times switching frequency is 200 kilohertz, sorry. So we got our number of turns equal to 3 for both primary and secondary windings. So then I'm going to design the planar winding, 1 layer, 1 turn. Then we have 3 layers for primary and 3 layers for secondary. So the next step is select the optimal copper thickness. First, we need to calculate the skin depth at 100 kilohertz. The skin depth equal to 7.5 centimeters divided the square root frequency. So we got a 0.24 millimeters. And then because we have 3 layers for primary as well as a secondary, so we can find out our optimal delta is around 0.4 from this graph, and this graph is from the Dauver's equation, as I showed before. So then we got our optimal thickness is 0.4 times delta is around 0.1 millimeters. So we can use 3 ounce copper thickness for PCB windings. Then so the next step, so we're going to draw the 2D view of the planar transformer. So we have this 2D cross section. We have 3 turns, 3 layers primary windings, 3 layers secondary windings. So then and from the top view, we have this mean turn length for each of windings, and then we can calculate our DC resistance. So this is straightforward. The DC resistance is equal to the resistivity times the mean turn length times the number of turns divided the cross section of the conductors, which is equal to the thickness times the width. So we have parameters given before, and here 112.4 is the mean turn length millimeters. This is the mean turn length of each turn. And then we have thickness 0.1 millimeters, and our width is 10.6 millimeters. That is from the data sheet. And we also give the 0.5 millimeters from the winding to the core for creepage distance. So we got a 5.3 millimeter for DC resistance in our case. And then the next step is to calculate the winding AC resistance. So we know our DC resistance, and then we apply the Dauver equations. We know our number of layer equal to 3. So from the Dauver equation, we can calculate the ratio of the AC to the DC equal to 1.07 here. And we also using the ANSYS simulation to verify this. We got the same results. And then so the AC resistance just slightly increased than the DC resistance from 5.3 to 5.7 milliohm. So the next step, we calculate our magnetizing inductance. We know our number of turns, and we know from the data sheets, we know the AR value, the inductance per turn. So here is 8.3 microhenry per turn, and and the magnetizing inductance is proportional to number of turns square. So we get 74.7 microhenry magnetizing inductance. And then next we calculate our RMS current. So before we calculate the RMS current, we need to calculate our ripple current, and that ripple follows the boost inductor ripple. So this is the circuit operation. So that ripple follows the boost inductor ripple. So from a boost inductor, because the boost inductance is given in 30 microhenry from here, and then when all switches are turned on, so the input voltage is clamped to the primary windings, which is 30 volts, and then the timing, the period for the first stage is duty cycle times T. The T is 200 kilohertz, the 1/200 kilohertz. So we got 2 amps for the ripple. And then we know the next step. So once we know this ripple, the next step is to calculate the RMS current of the winding, and we can use the RMS equations to calculate this. And then this is a formula to calculate the shape of this current shape of RMS current. So we get 12.9 amps for primary winding RMS current, and we also use the Plex simulation to verify our RMS current. So you can see here that both primary and secondary 12.9 amps RMS current. So once we know RMS current, so we can calculate our winding loss. And here, that because this is a transformer and we don't have a DC bias, average current is 0. So then we don't have DC loss because the DC current is 0. So we only have the AC loss. So RMS current, AC RMS current square times the RAC resistance is the winding the AC resistance winding loss. So we add both primary and secondary, we got 1.9 watts for the winding loss. And then from step 3, we got our core loss 1.1 watts, and then add them together, we have 3 watts in total, which is smaller than the maximum 3.75. So I would say, and you can see here the winding loss is nearly slightly higher than the core loss. So I would say this is close to the optimal design. So the converter is safe, and if you calculate the temperature rise using this 3 watts divided the thermal resistance 20 degree per watts, then you get a 6 degree temperature rise. If the ambient temperature is 25 degrees Celsius, then we get a 65 degrees temperature. So up to now, everything is fine. So so this is showing the step-by-step transformer design. But of course, if you look at the copper utilization, it is quite low. We still have a lot of space that that is remaining nothing here. So we can further reduce the window areas. If you can design your custom core, then you can further reduce that one. Or you probably can have more windings in parallel, like underneath. Then you can further reduce your winding losses. But here I'm not going to continue with that. Maybe if you are interested, you can continue to further optimize. So yeah, that's it. Thank you very much, and I would be happy to answer your questions.
We're going to do something. Tema, you are here. Recently, last week, we showed to everybody our new planar simulation tool from Frenetic. So I think this is a great opportunity to try to put the specs of Ouyang, of the example he has used today, and see what happens.
Yeah. By the way, I want to say we use a Frenetic tool to verify my result. We matched pretty well with your results. That's really good.
Thank you.
Thank you very much. Thank you. Okay, I'm going to try to be as fast as I can. So I'm sharing my screen. This is just for putting some context. So as you know, at Frenetic, basically we have an API, and this API is where we connect, let's say, all our technologies. And recently, we have developed a new kind of model that is called FEM, that is able to run finite analysis simulations using console on the cloud. And then on top of these APIs, we build products. And most people have been using our Frenetic AI for designing converters, or even this suggesting planar design, and our simulator for the simulation of magnetics. But we didn't have the option of a planar app, and this is exactly what is right now. So we added this new product that is a planar simulation app. So so now I'm going to go directly to the case of Ouyang. So as you know, using our platform, you can get the designs of the planner. But since Ouyang already did that, I'm going to jump directly to the simulation. So in this, for example, this is just an example I did actually last week. And in this example, also you can see the core losses, well, everything. But we are going to jump directly for calculating the design that Ouyang just did. So if we open our application and we take a look of them, so let me put here in parallel the specs. So we have the specs from Ouyang here. So the design parameters that he has been selecting. So I have prepared all these specs, and I'm going to put all the information here. So first, starting with the core. So I'm going to just describe here the core the dimensions of the core that we are going to use. So this is the planar core selected by Ouyang. Then this is not a round leg, so we have like a 7.9 here, and it's a rectangular leg. And then now I'm going to put the locate where it's going to be the PCB. So the PCB is going to be not right in the middle. So it's a little bit in the downside. So this is like 2 millimeters, and it's going to be located here. So you can move where the PCB is located on the window. Then I'm going to describe the layers. I mean the PCB. So it's 3 layers. This is an estimation of the distance that we took from the simulation to and also a approximation of the thickness, and also the distance between layers, 0.2. And for the secondary, the same number of terms, 0.5, 2, same thickness, 3, same part. We have, let's say, the waveform, and also now we have to we are I mean, this simulation runs in console. So we can choose the number of also the harmonics. So we're going to choose maximum, so 5. And we need to customize this because actually, I'm missing a layer, I think. Okay, this is one. Yeah. So now I can choose where is the location. So the simulation, we're going to put it like this. So the layer is in this position. I have, this is the way from the simulation, and then we can run this. So if everything goes fine, we will get some results of the AC losses. This is running, as I said, using console, our console module, and any user right now. Also, we have implemented the user's account, so we can offer personalized accounts for customers. That is something we didn't have before. And yeah, so let's wait how the things are going. Should take less than 1 minute if everything is fine. Okay, so there you got it. So it's 1.68 BAT of losses in the AC. And also we have the leakage inductance for this configuration and the capacitance. So if we review, let's say in the calculations that Ouyang presented, that was 1.9, is very similar. We analyzed the difference, and one of the main differences is the way that that we calculate the I will show you where. So moving from 2D, well, this is here. Moving from 2D to 3D. In this case, we use the quasi 3D approach from our researcher Richard. And the reason that is different is because in the explanation of Ouyang, he multiplied the 2D by the average length, and there is a small difference. But the values are, let's say, very, very close. But as you see, it's kind of pretty fast.